Alright, so today we are going to look at how we can implement the encoder and decoder parts of the transformer architecture from scratch. So when I say from scratch, that means we are not going to use the libraries, the neural network modules available in PyTorch. By that, I mean we are going to use the fundamental matrix operations, but we are not going to use linear layer decoder, layer normalization, and so on and so forth. Okay, so there's the objective. All right, so let's begin. Okay, so first we'll go ahead with encoder, and then we'll start with decoder. So I'm going to assume that we have an input x, and its shape is batch size by sequence length by the model, which is the embedding size. All right, and from here we have to build the complete encoder. So see, encoder has different parts. There's one encoder can have multiple encoder layers, and in each encoder layer there are many things. So we are going to build one block at a time, one piece at a time. And so first let's build the encoder layer. Okay, so right now I'm not talking about the positional encoding. We can add it later, but that's fine. All right, so let's assume that X is the input to your encoder layer. So right now we are implementing the first encoder layer. All right, so what do I need? I have X. Now what is the first step? Once X is fed to the encoder layer, what is the first step I need to do?
We'll have to construct key value query.
Absolutely right. We need to construct key, value, and query. So construct query, key, and value matrices. I should say tensors. Okay. So for Q, K, and V tensors, we are going to need first WQ, WK, and WV. All right. And even before that, we need some things. For example, what is D model? So D model, let's say it is 32. I'm just taking the example from encoder assignment. Then there is number of heads is, let's say it is 8. All right, so we need WQ. Okay, so I've not written the imports, but this is how we'll do it. Torch dot, sorry, not torch, uh, nn dot parameter, then torch dot. Uh, we are initializing the parameters from a random normal distribution. Then we have to mention the size. What should be the size of this WQ?
So size of WQ should be D model times number of attention, uh, D model upon number of attention head.
Okay, so what you're saying is what should be DQ, right? D model by number of attention. So this is D model by number of attention heads. And in this example, if we take the above numbers, it will come out to be 4. Okay, so yeah, basically we need this variable also, which is DQ, right? So it will be D model comma DQ, assuming that this variable is also available to us. Is that correct?
Yes, sir.
Okay. Anybody else? Any thoughts? Yeah, let me add one more thing, which
Just
is generator.
It should be normal. Is there anything that we...
Pardon me?
We need to initialize with the normal distribution also.
Right, right. So we are initializing it normal distribution, no?
Okay.
Let me increase its size.
Just a quick question.
Yeah. 0. It could be anything else. Yes. Go ahead.
Yeah, just a quick question. So, when we define WQ, can we have the number of heads also as a dimension, as in it's a three-dimensional tensor as opposed to a two-dimensional tensor?
Fantastic question. I'll answer this question. That's why I actually stopped here. Anybody else wants to attempt it?
We can also do like that. Here we can keep dq into heads, and after multiplying and generating query vector, we can again reshape it like heads into d model into dq.
Heads into demodeling Q. Okay, so what you're saying, we do it for one head and then repeat it for other heads, is it?
No, we can do it together for all heads. We can generate query vector for all heads at in a single in a one go, and after that we can split it for all heads and
Yeah,
do matrix multiplication q transpose k for separate heads separately.
So
that's right.
we can see that each of these W is actually a submatrix of the larger W, which is comprising of all the heads. So as Muhammad was saying, that is how it could be done in a single shot also.
Correct. So
Yeah, yeah.
yes, yes.
Sir, one second. Sorry to stop you, but it is for one head, right? The
Right
third
now
one.
it is for one head, but
Yeah, right now.
that was the question. That was the main point we are discussing. Can we do it? Can we define WQ for all the heads in one go, so that our code will look cleaner and it will be faster also, because there will be no looping. Not calculating Qs for QKV matrices for every head. That's the question, right? So the answer is yes, we can do it, and I'm going to show you how that works. You'll have to be careful about the multiplication operation between two tensors, especially when one of them is three dimensional or maybe higher, and the second is also similar. Then you have to be just careful about the matrix multiplication. Otherwise, yeah, we can do it. Okay, so let's say this is our WQ, and we can actually do it for rest of the W matrices as well. 2, and this will be Q, let's say K, this will be V. All right, just hold on a minute. This is very important step to understand how we can do this matrix multiplication, tensor multiplication for all the heads for an input in one go. Okay, so see, you already know what happens if the input has only let's say only one sentence, right? That's what we have seen. But right now what we are assuming that the input is of this size. So the examples that you have seen in the lectures are of this size, T by D model, right? So there is one sequence, and in that sequence there are D model uh, D model entries for every token. That's what we have seen in the lectures. But right now, when you are actually training your neural network or transformer, you are going to receive a batch of inputs, and that's what we are trying to do. Okay, so just bear with me for now. That we are trying to compute Q, K, and V for all the heads in single operation. Okay, that's what you want. All right. Now, what is the next step? We got our W tensors. Now what?
Calculate Q, K, and V
Absolutely.
using
Q,
the token.
correct. If we do it once, if we do it for Q, then others are just copy paste operations, right? So how we are going to do it? Torch dot.
Matmul, I guess.
First we have to reshape it.
Okay.
Okay.
Yeah.
Madmal is one way. Definitely. Okay, give me 1 second. I'll copy paste some import code so that we can see some quick examples of what we want to say. Okay. So why do we? Okay. So what we are trying to do is WQ is, so we know that we are trying to multiply X with WQ, right? Which is X is dimension BS by T by D underscore model, right? This is dimensions of X, and WQ has dimensions like heads, D model, and DQ, right? Now imagine that if I can get an output, just this is kind of our wish list, this is the output I'm expecting. So what if Q is something like this: heads by BS by sequence length by DQ, right? So if assume that we were doing it for single head, and the input had only one sentence, then the Q would have been of this shape. Is that correct? Yes or no?
For first batch, for first head.
Yeah, for first batch, for first. No, I'm not saying first batch or first head. Let's say only single head and only single input.
Yeah.
Single sentence is input, right? Single sentence. So T is the sequence length, right? So if we had only one input sentence and only one head, so this would be the shape of Q I'm expecting, right? Is that correct?
Yeah.
Yes,
Right?
sir.
But what I'm looking for ambitiously is I want to do it for all the heads and for every input in the batch. That's what I want to do. Okay. And now here comes the tricky part. So I'm not going to use MATML. I'm going to use something called IInsum. Is anybody aware of that? So let me create some matrices that will reshape, let's say 2,3. This is your A. Similarly, we can create B. So start at 7 and at 12. Okay. So A at the rate B, this is actually matrix multiplication. What is wrong? Okay. 7. Oh, it should be 30.
It should be 3,2, sir.
Right. I mistakenly reshaped it. 2. Right, now it works, right? Is there any other way to do it? So the reason I'm not going with MATML is because when higher dimension, it becomes slightly confusing where to unsqueeze it, right? I'm trying to show you a simpler method which will work no matter what are the dimensions of the tensors, and you can very easily manipulate them, and I'm going to show you that. Okay, so torch dot IInsum. I'm going to write, okay, just bear with me what I'm doing. You might see, okay, what is this magic? What? A comma B. I hope it works. So this is the output right now, right? So let me copy this. This is the output of your normal matrix multiplication, right? Now, what if I do something like this? It is still giving me the same output, right? So what I'm trying to do is I'm trying to implement the matrix multiplication with the help of this function IInsum, and it helps in with tensors when the tensors have large number of dimensions. So you must be thinking, what is this, right? So these are the two operands, A and B. These two matrices I want to perform some operation on, okay? And IJ these two characters represent the row and column indices. Okay, so you can see you can assume that ij for matrix A is the row first and second dimension. Jk for are the first and second dimensions for matrix B. The reason I am writing, you must be thinking J for the column for the first matrix and row for the second matrix, because they are exactly the same, right? So what we are trying to do is we are mentioning, okay, this is these are the dimensions of the inputs and these are the dimensions of the output. So when you write dash and less than sign, greater than sign, then it is saying that this is the output. Okay, and J is disappearing. So what I'm trying to say is, okay, multiply along this dimension J and output only I and K. So when you're multiplying along dimension J, add it, because that is disappearing, right? That is getting reduced. And just give me output as I and IK. Too complicated, is it? Okay, let's do something similar. Something simpler. Okay, so let's say IJ and I. That means what I want to do is I want to do a reduction operation on A. So the indices are I and J. Okay, and what I want is in the output I only want I. Okay, so the second dimension J, it will be summed across. Okay, because I do not want that. So we already know what is A. Right. So A is 0, 1, 2, 3, 4, 5. Right. Now what I'm saying is sum across the second dimension. Okay. That means I want the first dimension, but the rest of the numbers from the second dimension should be added. Okay, let's see the output. I think the output should be 0 plus 1 plus 2, which will be 3. And the output for this will be 12. Okay, so it will be a single dimension matrix with 2 elements. There it is, 3 and 12. We can do something similar with,
so this is another way of specifying the dimension.
Exactly. And this is going to be very useful. I'm going to tell you that.
And this is used only for adding up, or is there any product or other IN max or IN other thing?
See, there is limitation to the operations that you can perform with this one, but when you're multiplying two tensors, this is fantastic. Very easy to understand, and actually we are going to see that it can combine multiple operations into a single one. Okay, so
it's better readability. This has better readability, more intuitive.
Absolutely. And the importance of this will become more visible when we are going to multiply these tensors. Okay, so here what I'm trying to do is I am saying that, okay, there are two indices in my input, A and I and J. I want only the jth index, right? For the ith index, you just sum across, take sum of all the elements. So whatever index I am removing from the output, along that index, it will be the numbers will be summed across. Okay. Now let's see this.
So in sum, it will still work if we replace JK with KJ when we are doing matrix multiplication.
Here?
Yeah. If we replace JK. Okay.
No, it will not work. The reason for that is right now when I'm specifying this string, this operation string, that means I'm saying that the columns in the first matrix is same as the number of rows in the second matrix. Make sense?
Yeah. Okay.
Yeah. And this is important to remember, because see, when we are going to multiply these two things, W, Q and X, there is one common dimension, which is the model. All right. We're going to see that. And let's take a look at another example. IJ to JI. Right. What am I doing over here?
Transpose.
Absolutely right. So I'm transposing the matrix. So remember that when we will be multiplying Q transpose K, right? Actually, we don't have, when we are multiplying two matrices, two tensors, and one of the tensor has to be transposed before multiplying, then we can actually write the same operation without writing two operations in the form of two operations, but a single string. And we are going to see that. By the way, einsum stands for Einstein summation. So Einstein invented this way of writing mathematical expressions, but then it was adopted, turned out to be very useful, and it was adopted for all the matrix operations. Okay, so let's see that. All right, now you have seen that. This is what we are doing. Okay, now what I want to do is I want to multiply uh, x and wq, and the magic lies in the operation string, right? So the inputs, the dimensions of x are batch size, sequence length, and d model. So I'm writing it d. By the way, you cannot use multiple characters to represent a single dimension. It has to be a single character. Okay, so these are the dimensions for x. Now the dimensions for wq. It is h, d model, and it should be q, but okay, let's write q.
Number
Okay,
of
this
heads.
is number of heads, right? Right, this is the dimensions of wq, no? Heads,
Oh, okay,
d model,
sorry.
and dq. Correct? And now what I want is, I want an output, something like this. I want per head, per batch, per entry in the batch, per entry in the sequence, the its projection dq. Right? That's what I want. So I can very easily write it like, all you have to do is what the shape that you want the output in. This is the output I want, right? Okay, so all I have to do is h, then batch size, then sequence length, and q. That's all. The common dimension, remember that d is the common dimension, right? So these two tensors will be multiplied across that dimension, summed up, and then it will provide the output. Does that make sense?
Sir, can you say it again? This what is the role of this comma in the left hand side? BDD comma.
Yeah, the comma says the comma separates the dimensions of the two or more tensors that you are operating on. So there could be actually 3, 4, 5 tensors in here, and same number of dimensions you have to mention for every tensor array. Okay, let me give this with an example. Okay,
So
so
how does
let's
it
say
know that it has to do a multiplication or it has to just do a addition?
good question. See, the dimensions that you are mentioning in the input and which are there in the output, they will stay the same. The dimension which is you have mentioned common, like d have you mentioned that d model is the dimension that will be reduced, and you have not mentioned in the output, right? That means it will multiply these two tensors across this d model dimension, sum it up, and then produce the output. let
Okay.
me let me convince you. Okay, let me try to convince you in one more way. So let's say torch dot random, and size is, let's say, the exact thing, right? So this is our x. Batch size is, let's say, 10. 10. Sequence length is, let's say, also 10 or 8. Let's keep something else, just to make sure that we can identify these dimensions, right? And similarly, we get, oops, wq. Wait, I had taken d model as something else, no? D model should be 32, right? My bad. So batch size is, let's say, 10. 10. Then it is 8. Then it is 32. All right. And WQ size is 6 heads. I don't know how many heads did you take. Heads we took 8. Okay. For a minute, just let's say 7, so that we can identify which dimension belongs to the head part. Batch size is, my bad, it should be 32, and DQ is 4, right? Now I'm going to just write this over here and print q dot shape. There it is. Right? So you can actually manually verify also what it is doing by looking at the individual matrices.
Sorry, you might want to change it to 28, I think, then, the D model.
We
Because
change it to
you're splitting 32 into 4, right? So 7 heads. If you're having 7 heads, then you'll have to have 28 as your D model, right?
You're right. You're absolutely right. The only reason I have not performed the operation which will be followed by this, uh, which will
Okay.
follow actually. I just want to mention that right now I'm taking 7 heads and 7 is coming at the front, right?
Okay,
So
got
per
it.
head, yeah, that's what I want to focus. I uh, deliberately took 7 because that's a unique number in these 6 numbers. Okay, so you can see that head is coming at the foremost, the first dimension. Next is batch size, next is sequence length, and next is DQ. Right, so this is the important point to remember. If you go along with matrix matmal operation, then you'll have to actually change the second uh, tensor. You have to add one singular dimension after 7 and squeeze it and then multiply it. You can do it that way also.
So
But
wherever we have got 32 here,
Hello, sir.
it is taking a dot product adding depth only on that particular dimension only.
dimension, absolutely right. Yes.
Hello, sir.
Yes.
Can you show the normal way also? Like this is an efficient way. This is fine. Can you show the normal way, like matmal or something also?
Okay, sure. All right. So let's
Okay.
say
So what we have a two-dimension common in these operation, then which dimension to decide? Like how will it decide which dimension to take?
32 is the dimension that you want to compress, right?
Hmm.
So remember, whenever you are performing matrix multiplication, one dimension will get reduced. It will not be there in the output, correct? So earlier we were saying a multiplied by b, right? So 2 by 3, 3 by 2. So this one dimension was removed from the output. Actually, this is called reduction operation. Similarly, in here, when we are multiplying x in WQ, this dimension, D model, is being squashed. Make sense?
No, that is fine. Like for this particular use case, we are not encountering like two things which are like two dimension which are common. Like let's say there is a use case, particular use case. If I wanted to use this operation, where uh, let's say Q and Q are like Q is in both the cases, like BTDQ and STD, something like that. Q and
Okay.
something like that. So then, how this in sum will decide that which dimension to compress on?
Okay. Can you? I think I can help you understand that. But can you write the question two matrices? You know, with their dimensions. I think I'll take a look and let you know.
Sure, sure.
All right. So somebody asked, what is the normal way of doing this? So let's do that. So in order to multiply these two, then it will be torch dot matmul x comma wq dot unsqueeze squeeze dim equal to 1. I think this is the way to do it. Yeah. Dot shape. There it is. We got the same output. You can actually check that also. So let's call this Q1 or Q. Let's call it Q, and let's call this one Q matmul. Q underscore matmul. All right. For making sure that we are receiving the correct output, we are going to initialize it only once. Okay. And let's print Q 0 0. And similar thing, we put it over here. Have to make sure that It is not shape. All right, so let's do this. Q00 is this. And oh, not Q mat, it should be Q. There it is. You can actually verify that these two matrices are exactly same. And you can do this for all the elements. Make sense?
So, sir,
Yes, sir.
basically, unlikely matmal in some we don't need to take care of the dimensions like doing transpose and all these.
Absolutely. Absolutely. You don't have to do it. So that's why I particularly like Einstein method. It is less confusing and it will work wonders when you are trying to perform multiple tensor operations to get a quantity. I'll come to that part also. Okay, so any questions so far? So this is how we are computing Q value. And there are two ways we have seen it. One is Einstein. This is what I like personally. I'm going to use it for the rest of the tutorial. And the second one is the...
So can you explain what unskews is exactly doing here? That
Pardon me? Yeah, unsqueeze is actually inserting... Okay, we can see this. So basically it is inserting one extra dimension at position 1.
okay.
Yeah. So this is the classic method of doing it, but I like this Einstein method better, and I'm going to use it. So
Can I also try? Can I also do unsqueeze on X instead of WQ, like in the same position where the head has to occur, like in say the second position?
yeah, you
Will that
can.
also work?
So what you want to do is unsqueeze this part, is it? After
X, unsqueeze X instead of WQ.
unsqueeze X, it will not work, you know. I'm not sure.
Okay.
Yeah, let's try that. So instead of this, you want to do this?
Yeah, in dimension 2 instead of 1, I think.
Okay.
Probably.
See, this is the challenge working with MATML with and different sizes of tensors. Right? It's not very intuitive, to be honest with you, how it will work.
Right.
So I think it may be easier if you explain why are we doing this additional dimension.
See, if to be, I don't think so that I have very good explanation because this is something I've been studying about, and I think
I can attempt
I've
an
read all the
explanation if that's
documentation.
okay.
Yeah. So at this
I
moment,
can attempt it. I can attempt the explanation because the way MATML works is that it starts matching from the last dimension. So, like for
okay,
example, if there is 4, that 4 doesn't match with 32, right? So either 4 and the other side has to be 1, or it has to be a matching dimension. That's how MATML works. So either I have to unsqueeze, like for example, if I unsqueeze the last element in X, for example, then that 4 gets multiplied with 1, and then 32 match, and until that it kind of multiplies and then puts 10, 8 and 7 across it. So it basically just looks at from the right side whether all the dimensions are matching. If you
let's try 3,
3, but then 7 and 8 don't match, I think it will give you an error.
I see.
Right, whereas if you have 32 being like, so suppose you put dimension 1, for example, a dim 1 and multiply it, because here it is yeah, if you do 1, I think here also it may not 1. Okay, see here, yeah, so what it does is it pushes all the way till the right, so you have 32 and 4 right at the end. So it matches that 32, 4 goes against 1, and then you have inserted one more dimension. So it just basically goes from the right and looks for dimension match. I don't know if that's very clear, but that's the rule it seems to follow.
I see.
But you will get the same, I think the output should hopefully match with the other one you had.
Yeah, it seems to be matching.
Yeah.
Okay. Yeah. So yeah, I'll move on from this point and probably pick up this matmal sometime later. All right. So here we are. I hope that all of you understand that we are multiplying basically two tenses. So to get q values for all the uh, heads in a single go. Same thing we can do for uh, k and v as well. Okay. Of course, I have to replace this with v and k. All right. Now we are here. What is the next step?
Project the input x to this UK.
We have done that already, no? QKV.
Oh,
Dot vector dot product between query and key.
It
Right.
means scale dot
Basically,
product. Yeah.
we want the attention scores and new representation in Z's. Z is the, I think, variable name that was used in lectures as well. Okay, we are going to use that. So Q, we have to multiply Q K transpose. Am I right?
Hello, sir.
Yes.
Uh, I was actually trying this, like how to handle the heads. Like I was trying with GPT, and it was showing something like D model, like WQ, WK, and WV. These three weights, the size it was defining like D model, comma heads multiplied by DQ.
Okay.
Like it was not counting like in different dimensions, but in a sequence, like d model comma heads multiplied by dq, like that. So
Okay.
is that approach correct, or that approach is wrong?
See, neither approaches are wrong. Both approaches are correct as long as you keep the dimensions consistent across the your architecture, your layer. Then it is fine. You know, at the end, the output should be exact from both the architectures, both the methods. It doesn't matter whether you keep the heads first or the model first, as long as you take care of the multiplication of tensors well, then you don't have to worry about it. Both are fine. See, what's the problem? See, if I get Q in this format, then I could have done in batch size multiplied by heads multiplied by T by Q DQ as well, right? I could have gotten the Q in such shape as well. But then also, then I have to make sure that when I'm multiplying, performing the other operations, I have keep this structure in mind.
Okay, okay,
Both are fine. I don't see any problem.
got it.
Uh, all right. So now we have to perform QK transpose, right? So QK pose. So again, we are going to use IIT. The inputs are Q and K, right? So what is the shape of okay, Q is this is the shape of Q, and same is the shape of K, right? And which dimension I want to multiply across? This dimension. This is the dimension I want to squash, DQ. Okay. So what I'm going to write? First of all, it has four dimensions: I, J, K, L, comma. What should I do here?
Transpose K and then L, right? So it will be IJ, but LK.
Last one should be L. Other we can write anything.
Right. I, J, L, K.
LK.
Absolutely right. So this is performing transpose, and then it will perform multiplication also. What do I need in the output?
IJ and K.
IJK.
KK should be there, right?
Right, KK should be there. Okay, IJKL. See, this dimension is not okay. We have to be a bit careful.
For second, it should be like KL, not LK.
Wait for a while.
It should be other way. We have
Yeah,
K,
we don't need to
LK in
take
the beginning.
transpose here. Yeah, K and L.
Can we
Because
have
both
like
Q and K have same dimension, and we don't need to take transpose. So
See, IJK. So see, we all right. So this is one thing we have to be careful about. IJK are the first three dimensions we need from the Q tensor, and T is another dimension I need from the second uh, matrix, no, second tensor. So it should be named something else. And in this manner, what I'm getting IJK M. This will work.
sir? Please elaborate this.
Yeah, sure.
Sir, if you write this HBTQ terminology,
Uh-huh.
That will be.
I think that will be better.
Sure. Okay. So let's say this I'm some Q is
So,
in the shape.
is it like can we put multiple that hyphen greater than symbol in this string?
No,
Only one.
only once. But that's like an operation. It is saying left hand side is the input and right hand side is the output. Okay. So this is the dimensions of your Q tensor H, B, T, and this is the dimension of your K. Right. Now I'll tell you one small thing about this. So what we want in the output is HBTT.
Q,
Is that right?
HBQQ or
No, TT, no.
yes, sir. Yes, sir.
TT.
TT,
Okay.
yeah, TT.
So the last dimension is getting squashed. That's the one I'm using to multiply these two tensors, no? Okay. Now, we cannot have it like this because it will get confused which T belongs to which one. Okay. So just for the sake of clarity, we can use S over here and S over here. That's it. And you have multiplied, you have computed QK transpose. Does this make
So
sense?
in this notation, we don't have to do, transpose. It is to the operation itself. The transpose is getting
Happening.
realized.
Absolutely right. Absolutely right. And see, let's look at the other example also we were talking about. It was something, where is it exactly? There it is. So let's say I actually do this. This operation will be an error because the dimensions are not matching. Perfectly fine. What about this? Torch dot sum ij comma ij comma ij. Oops, no, not ij comma kj. Let's say this is the one, and I want I comma k, right? So 2 by 3 matrix multiplied by 2 by 3. We of course we have to perform the transpose of this, right? So instead of writing, if the dimensions were in agreement, I would have written jk, right? But the j dimension in my matrix is coming in second place instead of the first dimension. That's why I've written it like this, and the output is still going to be correct. Let's see. So before this, let's print a at the rate torch dot transpose b. Let's compare the outputs of these two. Okay, what is the mistake?
You got to give the dimension that is being transposed.
Oh, dim 0 is 0, dim 1 is 1. Okay, what? Must specify the equation string with at least one operand. Okay, my mistake. I did not give it the operands a comma b. Look at this. Exactly the same output. INSUM is doing two things at a time. So not only it is multiplying, but it is taking transpose also as it is necessary. Right? Similar thing that we are doing over here. So keep this point in mind. When you're multiplying two matrices, you don't have to even worry about the shape of the tensors, whether they are consistent to be multiplied also or not. Right? Q and K, they are right now, they cannot be multiplied directly. Of course, the last two dimensions of K have to be transposed. Right? So if you ignore this part, heads by batch size, you just assume that Q is sequence length by dq, K is also sequence length by dq, then K transpose will be dq by sequence length. And when you multiply two matrices like this, T by dq and multiplied by K transpose, which is dq by T, then you are going to get T by T matrix, right? But now we are doing it with multi-dimensional tensors. Hence, we have to be careful about. We cannot directly use matmul as we do it. But actually, in this case, matmul, the output of matmul will be much more clear because the first two dimensions, the batch dimensions are same. So the last two dimensions are called the matrix dimensions, and the other dimensions are called batch dimensions. Right. So since batch dimensions are same, heads by batch size, then that will be the first two dimensions in the output as well. And T multiplied by dq and dq multiplied by T will give you an output of T by T. I hope it makes sense.
So when we are using that unsqueezed thing, we were applying it on the W.
Right. Yes.
So, and we are applying it at the second position.
Right.
So essentially for the batch size, we are introducing this additional dimension.
Correct. Yes.
Okay. Now I understand what Abrar was saying, that, kind of aligning them for doing this multiplication. Okay.
All right. So I hope that you understand what we have done so far. We have computed Q K transpose. We can do one more thing: divide by torch dot square root of dq. Right, the normalizing factor. Once we have done that, now what do we have to do? What will be output of QK transpose, by the way? So shape of QK transpose?
K by K.
Pardon me?
It is K by K.
K by K or T by T?
T by T.
T by T, and
Head
heads size is also
Head
coming.
into batch size into T.
Right. Heads, batch size multiplied by T, and then T. So this is the dimensions of QK transpose. Now what do we have to do? We have to multiply it with
Square root of.
no. Before we have already multiplied that. Now what is the next step? Softmax, absolutely.
Softmax, sir.
Right. We have to take softmax. So attention is equal to.
Sir, one question in the dimension of QK transpose.
Yes, go ahead.
Yes, sir. You took heads cross batch size. I think batch size cross head make more sense, right? For a particular batch, we are taking multiple batch size. We can do that, right? We can alternate.
You can of course do that. But just make sure that the dimensions are consistent when you are multiplying the matrices. That's all.
Okay.
Softmax dim equal to and so on. Okay, so these are normalized attention scores. So basically these are alphas.
Sir, can you explain this softmax dimension?
Right. So
How to identify that it will be the last dimension?
okay. So just assume that this is not there. Heads by batch size is not there. So this is sequence length by sequence length matrix, right?
Yes.
Right. So what you are doing is so first row represents the first token. Attention with respect to first token, right?
Hmm.
I think this is something very similar we saw in week one. Okay, so we have a T by T matrix, and the first row is the token first token in the input, and the entries in the first row are the attention with respect to that token. Correct. So you have to if you normalize that the first row, then you'll have to take the softmax of all the elements in that row, right?
Yes. Yes.
Right, and that is what we are doing over here. So the last dimension, which is this one, across this one we want to compute softmax. So all the elements in the first row we take softmax, the second uh, row we take softmax, and so on.
Okay.
Makes sense? Yeah. Now what will the shape of attention? ATT, basically same as whatever the input was, right? We did not perform any reduction operation or anything else, just normalize the values. Now what do we do?
Multiply with the
Absolutely right. So attention, again INSUM will come to rescue, dot INSUM. We need to multiply attention by V matrix. So attention matrix has size, okay, heads by batch size by T. I'm going to name it something else S. Though B and T and S are exactly same. And what are the dimensions of V? Heads by batch size by T by Q. Yes or no?
is it case sensitive? This
Yeah, it is case sensitive. So capital A is different from small a. And what is the output we are looking for? Heads by batch size by sequence length by Q. Any mistake over here?
So one note here, sir, for
Yes.
the those dimension of the matrices that we want to multiply,
Mhm.
only those dimension will be same, which we want to merge with, right?
Merge with and remove. Yeah, if you want to remove them, so let's say there's one dimension which is coming in both matrices, and you do not mention it out in the output, then that is the dimension that will be squeezed. If a dimension is input in the input as well as in the output, that dimension will be preserved. So, for example, H and B, head size, sorry, number of heads by batch size by sequence length. That's what I want. Right, in the output also that's what I want, and at the same time what I want is, okay, so imagine that uh, for the sake of checking this whether it is correct or not. So attention is, let's say, single end single input, it will be T by T, right? Then you multiply this with K, sorry, V, which is of size
Uh, T cross Q.
correct, T cross DQ. So output should be T cross DQ. This is what you want in the output, no? So, see, this is the dimension which is getting squeezed. The last dimension from the attention and the second last dimension from the V. So these two things should be exactly same. So
So,
actually,
yeah,
uh,
there should
Then
be
it will
ST.
be ST.
Yeah,
absolutely right. This should be
ST.
S.
That's why the S will get merged
Hmm.
and fade away. Yeah,
Yes. Yes.
fade
Right?
away.
Makes sense? because this dimension T from the attention matrix, I want to preserve it. I want in the output also, which is coming over here, right? So that's why HBT is coming over here, and then HBSQ is coming over here. S is the dimension we are squashing, and this will be the output. Okay, so we have computed this multiplication also. And what is this? This is our Z. Yes or no?
Yes.
This is QK transpose V, right? After taking softmax.
Yeah.
Right? Okay. So this is the output of one attention head. Of course, there is one thing which we have, a couple of things we have to perform. What is the next thing I have to do? So what will be the shape of this, by the way? The shape of this will be heads by
Cross
batch size
batch size. Yes.
Batch
Cross
size
T cross Q.
by T,
5 T cross
DQ.
PQ,
TQ.
right? Okay. Now what is the next step?
Now we have to merge, I guess, first.
Absolutely right. We have to concatenate all the outputs of the heads into a single output, and then multiply it by the linear layer, correct? And then do the point-wise feed-forward network. Multiply it by or pass through it by point-wise feed-forward network. So now we have to do what we have to do is we have to concatenate. So your output should be something like this: BS multiplied by T multiplied by
D model.
model. Absolutely. Okay. So now how do we do this?
We can use in some.
Einsam?
Yeah.
No, actually, not this time. Or even if it could be used, I am not aware how to use it.
Something like permute or something.
Pardon me?
Permute, is it? Permute.
Yes, you're actually right. We can use permute. Z dot permute. How will we do it?
Also, we
So
can
there
use
are-
view.
Okay, give me 1 second. Let me explain the simpler method. Then we'll come to the permute method. Okay.
So can you explain this again, like from Z to output dimension?
Right. So see, DQ is what?
This is the per head.
The model by heads,
Hmm.
right?
Hmm.
Now what we are trying to do is we are concatenating the output of every head, right?
Okay,
So-
okay. D heads is multiplied, so that's why the model comes.
Right? Yeah.
Okay.
You can write something like D model is equal to heads star DQ. All right. So before we come to the permute method, I want to explain a simpler method. Something like this. For let's say I underscore head in I underscore head. Oops. For in Z. Right? And then
For each I head in the
I had in Z. Right. I made mistake. In Z. And then we do this and torch dot concat. And that's all we have to do, and provide the dimension. Which dimension we are doing this?
Yes. Last one.
DQ dimension, right? Which is the last dimension. So this I head is basically of this shape: batch size by sequence length by DQ, and we have many of these. So we want to concatenate. So batch size and sequence length is going to stay the same, and we are changing the representation size. So this is the dimension we have to concatenate across.
For
Okay.
I head in is it right? Not for I. Okay.
Okay,
The two
for
ends.
yeah, my bad. Okay, yes, I had in Z, and this will be your output. So this is one method to do it. Simple, easy to understand. There's another method to do it, which is permute. Yeah, so go ahead. How to do this?
We'll have to push the first dimension to the third point, right? So we have to bring the batch size first, which means
Okay.
one will become first,
Okay.
then 0 will go to the next one, right? No, sorry. 2 will come next,
Okay.
T, right? Then it will be 0 and then it will be 3.
0 and will be 3. Okay.
Then you'll have to do all this contiguous and stuff. So,
Okay. Then what do we do?
so you have to make this a contiguous array, I think,
Okay.
because then you have to create a view which will concatenate along the last
Okay.
time.
Okay. And what will that be?
It will be 1, 2, minus 1.
Right. So basically batch size.
Batch size, token size, D model, really. But it's a DQ into H or DQ into H.
Right. Either D model or DQ star.
Yeah, correct.
It's correct. So this is also correct way to do this, and this will give you the output. Everybody understands what is happening over here?
So partial understood. Can you explain this?
Yeah. So see, when we are permuting, basically we are changing the shape of the tensor without changing the data, but we are reorganizing it. Okay. So earlier it was the output of the output. This is the output we want, and this is the input we have. Heads by batch size by sequence length by DQ. This is the input we have over here, which is Z, right? But what we want is we want batch size by sequence length by D model. Basically, we want to eliminate this particular dimension, which is heads. So you have to be careful about how actually this is stored in the memory, right? So any tensor in memory, it is stored like a one-dimensional array, and you have to take care of strides, if you remember that. So we are, first of all, we are rearranging this. So what I'm saying is I'm converting Z to in this shape. So first of all, batch size, then sequence length, then heads, and then DQ. Okay, so I'm reshaping it. That's all I'm doing by permute. Make sense?
Yes. Permute till permute, it's fine. Then what contiguous do?
Right. So contiguous is going to create another copy of the tensor if the strides don't match. If I'm correct. So this is I read from the documentation. So see, the strides typically when you permute or create a view, you're not going to receive a new tensor, right? It's going to create. It is going to share the data with the original tensor. But when you use contiguous, it checks whether the original tensor has the same strides as the new permutation. If it is not, it is going to create a new copy of it, right? And then you create the view. Make sense?
Okay.
Does this make sense? How we are able to do this? BS by T by D
In
model?
case of D model, we can put -1. Is it?
Yes, we can do that. Not a problem.
Got it.
Well, you are mentioning 3. Any one place you can mention -1. No? Yes or no?
Yes, sir. Got it.
Yeah. And you understand why this D model is working over here?
Yeah, that heads multiplied by DQ is performed.
That is correct. But do you understand? So you have to remember how a tensor is stored in a memory. It is stored like a continuous one-dimensional array. That's how it is stored in memory. So for every batch size, for every sequence length, that means every token, you can see every sample, every token, it is going to write the, okay, look at this one, write the output of one head first, then the second head first, and the third head first, right, and so on.
Got it.
Correct. So what you can do is you can actually read them together into a single dimension. Basically, you are concatenating them.
Yeah, like kind of what I was asking you previously, that thing, like this line is doing like at the end in the output level.
Right. Right. All right. So let's move forward. We have done this. And
So,
what is
so
next? Yeah.
when we are doing permute, we are mainly taking transpose. So instead of permute, we can use jet dot transpose, or also we can use einsum to take transpose of jet vector. Then we can
Um,
concatenate and do same thing.
you can definitely use Einsum. If you want to use tosh.macmul, then you have to do the transpose multiple times. No.
No, sir. Here, sir, when we are doing permute,
Uh-huh.
so we are just taking transpose of 1 and 0.
No, 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 no. See, the original, if okay, this operation will not do anything basically. Permute 0, comma 1, comma 2, comma 3. This operation is not going to do anything because what we're
Yeah,
saying, zero dimension comes at zeroth place, first comes at first place, and so on. So this is not doing anything. Now, when you're putting zero at third position, right, and one is coming over there. So when you're transposing, you can change
yeah. Yes, I
this thing
understand. In this case, we have to do 2 times transpose.
multiple times. Yes.
Yeah.
All right. So now we
So
are.
can you explain the dot T transpose and another like transpose function with dimension, how these two works?
See, when you're transposing, it is only so. Look at this. What we are doing is 1, 2, 0, 3. We are changing the position of all the dimensions. No,
Okay.
but when you're transposing, you can change only two at a time, and then they also, they get exchanged.
No, no. In the context, like the permute thing, I have understood. Like I am
Mhm.
asking that one, like two type of transpose. One is dot T, and another is transpose function with some dimension, zero dimension one. That thing.
Okay.
So like how? So when can we use dot T and when can we use transpose function?
See, dot T. I'm not sure how it will work with tensors. I've not used it. For tensors, since we are dealing with multiple dimensions, 3, 4, it needs which two dimensions you have to transpose across. So let's say z dot transpose. So you have to mention. Oh, sorry, not z dot transpose. Tosh dot transpose. And you write this is the matrix that you want to transpose. Dim 0, the first dimension that you want to transpose, let's say 0, and dim 1, the second dimension that you want to transpose. Okay, and the output of this will be exactly same as z dot permute 1 comma 0 2 comma 3. These two are
Yes.
exactly same.
So a permute thing, I understood. The dim zero, dim one, that thing I did not get.
It's fine, you're just mentioning the two dimensions that you want to transpose.
Oh, okay, okay, okay. Got it.
And sir, can you again explain the contiguous? What is it?
So contiguous, okay, let me torch.
Okay, so contiguous will not change any shape or anything, is it?
It creates a copy.
Okay.
See this one. So uh, again, you can verify this that it returns a new tensor if the strides are not matching. If they are matching, then it returns this tensor with the, again, the data anyway is not changing. The original data and the permuted data, it is actually the same. But if the strides don't match, then continuous is going to give you a new tensor.
Okay.
All right. So we are here. Okay, we have discussed a lot of things. Now we have the output of uh, attention it. What is the next step? We have concatenated. What is the next thing that you have to do?
Pass through a linear.
Linear.
Pass through the linear layer. Right. So again, einsum tosh dot einsum z by, let's say, W underscore O, and this W underscore O will be something like torch dot tensor. Oops, not torch dot tensor. Nm dot parameter torch dot. Uh, what will be its size?
D model
D-model.
plus D model.
Correct. D model cross D model. D model and generator I have not mentioned, but it's okay. Right? And what will be the operation string? So Z has batch size T by D model, right?
Correct.
Now, which dimension we want to squeeze? The first one, right? This one, and the last one of the Z. So the
D
operation will be
DS
DS, and what will be the output?
BTS.
BTS. Correct. Okay, so we have reached here. Now, what is the next step?
Pass throughs are point towards feedback.
Right. Before that, if you're absolutely right. But before that, if you look at the architecture, you'll find layer norm plus residual connection. Correct or not?
Yes, sir.
Yeah. Yes, sir.
So what should I do over here? Out was equal to
So
out plus what?
this much is multi-head attention is finished, is it?
Pardon me?
Like multi-head attention part is finished by
Yes,
this.
it's multi-head attention. No, not exactly, I would say, but just be with me. So we have concatenated and passed through it the output layer. That's what we have done. If you look at the paper, you will find residual connection plus layer now. So what do we do now? So that's what we are trying to add over here.
Out plus X.
Out plus X, fantastic. Then what? Layer now.
Leon.
Okay. How will you do that?
Gamma times out this.
Yeah, let's write the shape of the out. Out. What will be the shape of the out? Batch size by sequence length by
Yes.
the model. No? Yes or no?
Yes.
Yes, sir.
Okay. Now, what do we do now?
Out is equal to gamma times out plus beta.
So we have to perform layer norm now. How will you do that?
You can pass also layer norm, nn dot layer norm.
I can do that any other way without using that. Okay, so what we need is we need two things, mu and sigma. No? If we compute mu and sigma, then we subtract it from the original tensor, and then we need gamma and beta, which are the two variables from the part of the neural network, which can be adjusted. So how do we find mu? So assume that this is your matrix, or tensor that you want to perform layer normal. How can you do that?
Mean is the
Pardon me?
mean we will calculate, right? So,
Sorry, can you repeat that?
am I audible?
Yes, you're audible.
For mu, we will calculate the mean. I mean, the tensors.
Yeah. What? So okay. Torch dot mean. What next? Out. Important thing is dimension. Which dimension?
So, root, I mean, the launch, D model, I mean, each,
Should be -1, right?
the D model. So, for each token, we'll have a representation. So we will calculate all the elements in that first row. Then we will sum it up and divide the number of which is the model.
Correct. So I'm going to use keep dim is equal to true, so that the rest next operation will become easier for me. Same thing I'm going to do for
What is skip dim?
pardon me.
What is skip dim?
Keep dim is going to return me an output or the mean in the same shape as the original tensor.
Okay.
This will help me perform the operation. I'll show you. Okay, so instead of mean, we need variance. And what is the next thing? I have to perform out minus mu, right? Divided by
Square root of variance.
sqrt var plus some small value, right? Let's say minus 6. That's what we have studied, no?
Yes.
Correct. Okay. And this is your out, but just not yet. What are the two variables we have to associate with this?
Gamma and beta.
Gamma and beta. So what are the dimensions? So gamma and beta, again, they will be part of the network. So what will be the shape of gamma? So in different places you will find it initialized different, but okay, let's just start with ones. What will be the shape of gamma?
The same as var, like whatever is the
Okay.
dimension of var.
And what will be the shape of var?
The same as out right now because we're doing keep them, which is bs cross t cross d model.
Think about it. So if you remember the slides, you will find that for one sample, one row, whether it is batch normalization or it is layer normalization, you will find that there's single gamma for that.
So in that case, it's just a scalar.
It should be bs cross t.
Pardon me?
Bs cross t.
Bs cross T makes more sense. T is definitely. So imagine that you don't have batch size. You just have T by D model. So something like this, no? 1, 2, 3, 4, 5, 6. Imagine that this is these are the two inputs in your sequence. That's all. One is this, second is this.
2 3-dimensional words.
Yeah, 2 3-dimensional words. That's it. Correct. So forget the batch size for now. So what will be the size of gamma and beta?
Gamma should be like same dimension, I think.
See,
If I'm
for
not wrong, we are doing this scaling of that just right, so the 1, 2, 3.
right sample, correct.
It should be a scalar only, right?
But for the second sample, you are going to use the same scalar or different scalar? You are going to use a different scalar.
Okay.
So the size of this should be basically T.
T or bs?
Batch size.
Is it different scalar for different words?
Give me 1 second. Just a minute. Yeah, I'm sorry. There is actually I have to attend to something else. I will leave this to you for trying it out. But I think it is easy for you. All you have to do is out minus mu multiplied by gamma and add by beta. You have to figure out the dimensions correctly so that the operation can be performed seamlessly. Okay, so one quick thing I want to ask of you. So this is the one encoder layer, no? When the output comes out, the whatever the out comes out over here, then it is passed to feed forward neural layer, and then that is the output of your first layer, right? So imagine that we are not doing this. Okay, for a minute, I'm just removing this part. No layer normalization. Okay, and no, of course, residual connections also. Okay, we have added that. Let's remove that for now. Now, what you have to do is you have to pass it through the feed forward network. What will you do now? So it will be something like, so first of all, you need W1 of some shape and B1 of some shape. Similarly, you need W2, we'll see the shapes also, and B2. So W1 will be of what shape?
D model, the model.
Right, D model multiplied by
The hidden layer size, whatever.
yeah, 4 times the hidden layer size, which is typically this, right? And the shape of this will be 4 times
D model.
D model, and the shape of this will be
4 times D model.
pi D model. Correct? We are projecting it down back. So 4 star, and this will be this, and B will be D underscore model. These are the shapes of the matrices, and then we have to multiply them. So torch dot find some. We have heads by batch size by T, and then D model, right? And this is D by, let's say, E. The output that we are expecting is heads, batch size, sequence length, and E, projection on the higher dimensional space, and the inputs are out and W1 and plus B1. Correct? Yes or no?
By the way, sir, heads are fade away, so it's BTS now, right?
Oh, you're right. You're right. Heads are not there anymore. Correct. So this should be the output. Batch size by sequence length by the higher dimension. Then what you do? Oops. What is the next thing? You pass it through.
Outputs.
Again.
No outputs.
Achha,
You
okay.
take ReLU.
Softmax, right?
No, not softmax. You take you apply ReLU function. No?
Yeah, really function is, sir.
Yeah.
Then again through the second layer.
Right. So torch dot ReLU is what you do. So this is yeah. So this is the output of the intermediate layer. Then you do the same thing, but this time with W2 and B2. Right? Yes or no?
Yes, sir.
Yes, sir.
Okay. So this is the output of your first encoder layer. Congratulations. right? So we have reached that place.
Sir, one question. You used 4 cross D model there in the W1. So any particular reason why we are using 4 cross D model? Because it's repetitive, like every
Uh,
time we use it.
Actually, it was found from practice, and sir also mentioned in the lectures that typically this is the case, that uh, the size of the hidden layer in the FFN is 4 times the D model.
Is there a particular reason for 4 times D model, or is it just a convention that we follow?
I think many of the things that you'll find in the architectures is researchers experimented with different designs and found something to be more useful, and they kept it.
Okay, so some work better than the others.
Right, right.
Okay, got it.
So, any questions so far? Okay, we have gone through great length to come to this point that we have computed output of one encoder layer, right? Now, this out will become X for the next encoder layer, and you can actually stack many of them. So wherever you are seeing that these are the initializations, this if you are going to put this into a torch module, you are going to see that this will go inside the init method. Uh, this will also go inside the init method, and this will also go inside the init method. D heads and D model, this will also go inside the init method, and rest of the statements that you are seeing, anything that is performing operation, that will go into forward method, right? Even this is also will go to forward method. This will also go to forward. So all the operations, they will go to forward method, and all the declarations will go into init method. So that's how you are going to create one encoder layer. Now, if you are going to create one encoder in which there are multiple encoder layers, what you can do is you can use the module list from Torch library and keep multiple encoder layers there. And when you're performing the forward method, you have to pass through every encoder layer. So that will become your encoder. Make sense? Any questions? I'm going very fast, I know. All right, only one thumbs up. What about the others?
Sir, like I miss this W1, B1, W2, B2 part. Like exactly.
Okay, I'm going to request you to just look at the slides once, because I want to cover very important part next. Okay, just do that. It's very simple. You'll get it just by looking at it. Okay, the second thing is not relu. Forgive me for this. This is not relu. It is like this. Okay, so this is the part of the output of the first encoder layer. What about converting this into? So this is the code for encoder layer. I hope you understand that. What about I want to convert this into multi? So right now it is multi-head self-attention layer. Can I convert this into multi-head mass detention layer quickly? Is there a way to do so?
Need to multiply a mask with that.
Add the masked matrix with that.
Absolutely right. Absolutely right. So all I have to do is everything is going to stay the same. Add the mask, which will be added over here. Assuming that you have initialized the mask appropriately. And how will your mask will look like? It will have 0, comma, minus infinity, and so on, right? And so this is your first row. Second row will be 0, comma, 0, comma, minus infinity, comma, minus infinity, and so on. Whatever the dimensions are appropriately like this. Correct?
T cross T, sir.
Yeah. Okay, so it's a lower triangular matrix. The lower entries are 0, and the other upper half entries are minus infinity. And this is your multi-head mass detention. No other code is going to change. All right.
Yes.
Yes, sir.
All right. Okay, great. Now you understood this. So what is the input of encoder layer? Let's say you have one encoder layer. What is the input of encoder layer? The
The
X,
embeddings of
the embedding, right? The batch size by sequence length by embedding size, right? That is the input, which is the X. When you, what is the input to a decoder layer?
Output of the encoder layer.
No, 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 no.
Cached encoder layer.
You are right. You are right. Decoder layer, the output of encoder layer is definitely input to it. What about the multi-head masked attention layer? What is the
And the
input?
sequence length, like batch size cross sequence length.
By size by sequence length by embedding, right?
Yes.
The first word is go that goes into it, right?
So the QK transpose dimension is heads multiply heads batch size then T cross T. So and mask will be T cross T.
Mask will be definitely T cross T, yes.
Okay, so okay, summation will be like
Right. Then we when we perform softmax, the top entries will become zero, the other entries will become non-zero. Okay, so this is what I want to mention is if you get the encoder layer code correct, then going to the multi-head mask detection is very easy. All you have to do is add the mask. Okay. No, now my point is, see, the input to multi-head mask detection is what we just talked about, right? It is taking batch size by sequence length by embedding size. That is the input. That's the only input. One tensor coming to multi-head mask attention. What about the, now I'm going to convert this into multi-head cross attention. How can we do that?
Just retain the query vector from the x input as in the decoder layer, and take the key and value vector from the encoder layer, right? And
Absolutely right. Absolutely right. So the input to this is, there are two things which are the inputs to this.
So in the multi-head mask notation, so we take a X embeddings as an input, and based on that we project the QKV. But in multi-head cross attention, the query will be based on the embedding input. I mean, sorry, encoder's
Correct?
output.
You're
And
absolutely right. Just hold for 1 second. I want to add a point, and I want to
yeah,
I want everybody to pay attention to it. That in the multi-head cross attention layer, input is coming from the encoder plus the previous layer, multi-head mask attention. So it is going to take inputs from two layers. Okay, just keep this point in mind. And when we are doing these operations, right? WQ, WK, WV. This is encoder input. Encoder. No, am I making some mistake? Yes. This is the D. This is your. This is coming from multi-head mask attention layer. Query is coming from there, right? Yes or no?
Yes.
And this X is coming from encoder layer. Okay, so this is where you have to pay attention. Is this clear?
Yes, sir. Sir, is it okay to have a different sequence length for target and source language?
Sequence length for target and source language. Okay, that's a great question.
Like D model, we can keep constant throughout the model.
Right, D model has to stay
Yeah,
constant. You can definitely change the vocab size for input and output
yeah,
embeddings.
that's what I am asking, sir. Vocab size and sequence length.
The vocab size you can change easily. That's not a problem because you have
Yeah,
a,
that's final output.
yeah, that's an embedding matrix, right?
Yeah.
Uh, for the sequence length, I have to check on this one, Vishal. So I hope that you have gotten the grasp of what are the main components of the transformer architecture and how to code them. Of course, there are tiny details we have not covered here yet. For example, how would you add the positional embedding? How will you add the uh, embedding layer? Okay, embedding matrix basically. How can you do that? But I think you can figure it out. And if you still need help, I think the that document, that link, annotated transformer. Basically, it is the solution for your programming assignment 1 and 2. Okay, just do not use the linear layer and do not use the layer now.
Sir, for the question that this the question was the input in the decoder layer and input in the encoder layer could have different sequence length or not. That was the question, right?
Right.
Yeah. So for that, sir, in that can you share your screen again, please, for a
Okay.
minute? So
Yes.
for here that, sir, QK transpose, we can see that HBTQ and HBSQ. So T is the context length in the decoder layer that's been
Hmm.
given the input, and S is the context length in the encoder layer, right?
Hmm.
And after that, if you multiply it with the V vector, capital V,
Hmm.
then it will the S will again fade away, right? And
Right.
the Q will remain. So we can, I guess we can change that length, right? So it doesn't matter, it will give the same matrix again, HBTQ. So
Hmm.
can you go down a bit?
Yeah, maybe sir. In that case, we have not the D cross T matrix, like
Yeah.
not the square matrix. We will get the rectangular matrix.
Yeah, so in the Z, while we are calculating Z in line number 35, the HBTS is been multiplied with HBSQ. S is the context length in the encoder part, right? So S is getting fade away. So we are getting the T. T is the input context length of the decoder there. So I guess it's working fine.
Let me check on this one. See, the reason I'm saying this is
Mhm.
I'm not sure if it is followed in practice or not, because typically what mathematical conventions do is that in the vocabulary they will involve a null character. That means there was input to the decoder, but the output is null, right? This way, the model is able to handle uh, the mismatch in lengths of input and output. So let's say the input is of 5 characters, sorry, 5 words, and the output is only 3 or 4 words. In such cases, the model is able to handle it because it can output null a character. That means no output at all. So yeah, let me check on this one. I've been reading. So Prashant, I know that you asked this question before as well, but I've been reading up on this one, and let me get a very clear answer for this one.
So this null character can appear in between the sequence or at the end of the sequence.
It can be in between the sequence also, in between the output sequence.
Yeah.
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 All right then. Let's close the session.
Just
Have a good
a
night.
quick
Yeah.
final point. Sorry to hold. In the programming assignments, though, we had to tweak a little bit. Like, for example, if the layer norm is already given in the collab itself, so we have not implemented the layer norm because it was there in the collab. I hope that's okay.